Swayam Prabha. Digital India. Educated India.
Okay, good morning again. So we are talking about life cycle assessment or life cycle analysis. So this LCA analysis is done as per some ISO standards, and the main scope of doing this is that whenever you do something, a process, a product, a service, we are not just only looking at its functional role, but we are also looking at what are the impacts of these activities to the environment. Okay, what is the energy material requirements, what are the pollutions, what are the emissions, what are the waste generated. So I think this is more of a more integrated approach to justify ourselves that whatever we do, products, processes, services, are something that is sustainable, something that you can do over and over without really depleting natural capital. So in that line of thoughts, we presented few examples in the last class. We are talking about some plastic resins. I think I presented PET resin as well as PLA resin. And then we looked at these 4 different steps. Okay, first we set up the goal and purpose of doing this. Why do we want to do it? What are the goals? What are the boundaries? Right? So then we make assumptions. Okay, are we talking about cradle to gate approach, cradle to grave approach, or cradle to cradle approach? And then various other database, inventories, all that goes in. And then finally, basically we have a comparative statement. We can compare between different plastic resins and then look at which of them give more sustainable outcomes and which are more could be harmful. So we can actually have a better judgment of which material we should be using. Okay. So compared to PET and PLA, as per the resin, okay, just about the resin formation alone, we saw PLA seems to be more sustainable than PET. Okay. So that's only cradle to gate. You are only just stopping the analysis up to the formation of the plastic resins. So now we extend that approach further down. Let's say you take this resin and make some products. Now we are entering into another level of processes, and again we have to look at, okay, up to resin it's fine, but what about the products? Okay, so whether the conclusion remains the same. When we make a product out of PLA and PET, can we still say PLA is better than PET? Okay, those are the questions we want to ask, because up to resin making the processes are different. When you make a product out of these material, you have entirely different kind of processes, impacts. Okay, so therefore, when we talk about these plastic products, we often include the end of life option also. Okay, we think about the product and then what happens to the product after use. Okay, are we going to do landfilling, incineration, waste to energy, composting, recycling? Okay, so if you include that, then you can actually have a better judgment about what we should be doing. Okay, so that's the context what I want to talk about today. Today I will take one particular example of sustainable packaging, especially food content, disposable food containers. Okay, we all relish biryanis, right? We all order biryani. It comes in a container, right? And after we use, mostly we discard them. We don't really recycle. We don't really take care of it, right? So packaging is very important. So I'll talk about I think maybe 4 different kinds of LCA analysis done by different agencies, different software, different companies, and then you will see that largely the conclusions are quite inconsistent. I mean, what you can judge from one analysis, you can prove something opposite in another analysis. This is because the assumptions and boundary condition scopes could be a little different. Okay, as we are all chemical engineers or engineers in general, we are all used to calculate things, right? We actually do some calculation, we do some material balance, we do some energy balance, then we have boundary conditions, initial conditions. Our results largely depend on these initial conditions and boundary conditions. Same thing here also. Okay, the analysis can give you different results if you change the boundary conditions, assumptions. Okay, so don't get perplexed by looking at all these 4 categories, which all show different outcomes. They are showing different outcomes not because they are inconsistent, it's because the boundary conditions are different. So that's why setting the scope is very important for LCA analysis. Okay. Okay, so with that introductory remark, let's go back to the lecture here. So just a few remarks which we have already said before. Plastics are used for various applications. Okay. Among these, the packaging application dominates the entire plastic industry. Okay. Roughly about 30 to 40% of the plastic produced are actually going to the plastic packaging applications. Okay. So therefore, if at all we want to talk about sustainability, maybe that is the first thing we should look at. Can I come up with a sustainable packaging material? Because that's where a lot of plastics are being used. Actually, the packaging material is the one that is also have a shorter life. The moment you open the package, the packaging material has no value, it's thrown away. Okay. So large volume, short life, can we replace them with sustainable material? So that's a context. Now, when we say sustainable packaging, what are the options we have? Well, we can think about using plastics sourced from biomass or renewable sources, which we call them as bio-based plastics, or maybe recycle a plastic. If the plastic is already used, can I recover, reuse it, put it back into the same use, so that you don't depend on the virgin plastic anymore? So that is also one sustainable approach. Okay, sustainable material doesn't mean it has to be always bio-based material. It can also be recycled also. And the purpose of doing LCA typically is to compare between, if I want to make the same product with the 3-4 different kinds of material, one could be bio-based, other can be petroleum or fossil based, something can be recycle based. So these are the choices you have. When you do LCA analysis, you will be able to say which material option we should choose. Right. So that's why the LCA becomes a very important framework to make a decision about how we can translate to a sustainable packaging industry. Right. So here is some example. If I'm thinking about bio-based polymers, then we are talking about PLA, polylactic acid, PHA, polyhydroxyalkonates, TPS, thermoplastic starch, right? And then if you think about recycled options, we have PET recycled, HDPE recycled, and then to some extent polystyrene PP also. Okay, so these are all petroleum based products, but still if you have a good strategy to recycle this, you can also put it back into this. So when we do LCA, we are trying to compare, if I make a container with the PLA versus PET, or PLA with recycled HDPE. Okay, so you can make different combinations and then you can look at what are the best choices for us. Right. Now, here I am going to talk about 4 different LCA studies. In all of them, we still follow the 4 steps. We will set up the goal. Since this is about sustainable packaging, our goal is to determine environmental impact, energy needed, waste generated in the production of sustainable packaging, plastic packaging with either bio-based and or recycled plastics. Okay, so that's largely the goal. And we often do this cradle to grave approach because once you make a product, this product is used and then discarded. So what happens to the discarded product? Okay, so we need to look at whether it is recycled or incinerated or energy converted and so on. So once we have this situation, then we can compare the impacts, the environmental impacts of products made up of, let's say, virgin plastic, PP, PS, PLA, PHSA, etc., etc. Okay, and then we try to kind of justify or decide whether bio-based recycled plastics are better compared to virgin plastics. Okay, that's a kind of goal that we wanted to set. Okay, so now for all the 4 studies, I am grouping the goals in one slide, so I don't repeat it again and again. Okay, so largely as far as the sustainable packaging is concerned, for LC analysis, the goals are typically set like this. Okay. The second thing is about inventories. So if you may recollect that inventories means that you have to know what are the material, energy, water, utility that goes into the process of making the product. So now if I want to think about a product made up of PLA, I have to start from producing PLA pellets itself, which we saw in the previous classes. Okay, you might have seen this diagram. where we think about production of corn, harvesting it, drying it, processing it, transporting it to the wet mill, and then there you do dextrose sugar production, then lactic acid production, then lactate production, then polylactic acid production, and then making into a granule. Up to this we have seen. But in this case, if you want to make a PLA product, the procedure does not stop here. It continues further, going to pellets to extruding the PLA pellets into a plastic container, whichever shape that you are thinking about, cups, plates, boxes, containers, whatever it is. Okay. So, once you make these containers, you basically pack them into trays, and then you transport these trays to some retail outlets, okay, maybe Sangeeta or Talapakati, okay, you take to the containers, and then the consumers use the PLA container in their home, they unbox it, they consume the whatever that is packed, and then also about collecting the compostable plastics for compost incineration. So, you see the end of life is also included in this step. We are not just only not talking about production of PLA container, but also production in the plant, transporting it to the consumer is doing something with it, he is packing with something else, then he is giving to an end customer who is actually consuming the product, disposing the container. And then there should be another mechanism by which that container is collected after use, municipal waste management systems or other way of collecting it. Then what do you do with this? Okay. So, again you have to transport to another facility where it can be incinerated or composted or landfilled, whatever it is, right. So, this entire thing is what we call it as a cradle to grave. Cradle is here, we are producing somewhere here, grave is the final end of life options. In this entire thing, we want to assess the impact. So, here I was giving an example of PLA, which is a bio based. Let us say if I have a PET container, same container, instead of PLA I can make it with PET also. Again we start with how PLA is made. Again you start with the natural gas, crude oil, formation of ethylene, ethylene oxide, ethylene glycol, and then the terephthalic acid, and then reacting them esterification into a PET, and then granulating it, and then you basically have PET granules. This we have seen already in the case of PET resin making. So, now you do not stop here, you take the PET, transport to another facility where it is extruded into a container, and then again the containers are packed, shipped to the retail outlets, and then the consumers use the PET for packing something, and then again collecting it, and then dealing with the end of life. So, the steps for the grave, cradle to grave are same for PLA and PET. Okay. You see the only difference is this: in the resin making there are some differences. Okay. So, now we are taking things together in the formation of the resin to formation of the product to what are the end of life. Okay. So, all that is taken into account. So, when you think about inventories in the second step, okay, the database that we are going to use should have all the information related to this, right. It is an enormous amount of information that is needed, right. Then third step is to look at impact assessment. When we do impact assessment, we often define a functional unit. What is a functional unit? It could be a cup, it could be a plate, it could be a container, it could be anything that serves a particular function. Then you also do some normalization. You say, okay, I want to make 10,000 such functional units, or maybe 1,000 such functional units. So, that is your basis. For that basis, you calculate, okay, how much energy, water, greenhouse gas emissions, waste generated, pollution generated, acidification, eutrophication, various other polluting, heavy metal contamination, etc., etc., etc. Okay. So, those are the impact assessment that is done. So, that is step 3 as per the ISO standard. Then step 4. Step 4 is how do we interpret this data? What do we make out of this? What are the conclusions we can draw? So, here again we have to make sure that the goals are achieved at the end of the LCA cycle. That means the database should have adequate information to calculate the things that you wanted to calculate, that is set in the goal. And then we also have to check whether the database is consistent in terms of comparing with similar set of data sets, regional specifications, etc., etc. Okay. And then also sensitivity analysis. What if there is some error in some of the data? How does it conclude, change the conclusion? So, sensitivity analysis is also part of the LCA analysis. So you can see that as far as the sustainable plastic packaging product is concerned, we have set out all the 4 steps. Okay, setting up the goal, deciding the inventories, impact assessment, and then interpretation. Okay, so now I am going to the specific cases of each study, in which case I will not show each step again 1, 2, 3, 4. We will largely look at the impact and then conclude what we have learned, right. So the first case study is to basically looking at the goal is the following, that what are the environmental impacts of polystyrene, paper and PLA based packaging material. Okay, so material choice is given, and this particular study is from Franklin and Associates, and the reference is given here. So here they talk about formation of cups, plates and clamshells. So the clamshells are basically this kind of dabba you have seen, right? You can close and open. You would have seen this kind of containers for let's say storing fruits, sometimes even sandwiches also. So those are called clamshells, and the materials are here. As I said, polystyrene, could be paperboard, it could be PLA. So this paper, this report actually gives a lot of data for cups, plates and clamshells, but here I am taking only the clamshell approach, clamshell as an example. So what are the assumptions? So the calculations are done for 10,000 clamshell containers, and they have taken 2 materials in this particular clamshell, that is general purpose polystyrene and then PLA. Okay, so one is fossil fuel based, another one is bio based. So here they did not consider PLA's composting. So PLA can be composted as one possible end of life, but they did not include that in this analysis. So that means whoever is going to make this clamshell with PLA or with the with PS, they are not looking at composting as an option. It has to be something else. What is that? They are talking about cradle to grave analysis with a choice of 80% of this end use will be landfilled and only 20% is converted into energy. Okay, you burn this, incinerate it and then generate energy out of this. So this end of life choice, you may say why 80 to 20%, why can't be 50-50%, right? So this largely depends on where this container is used, which government agency or which local government agency is going to handle this waste. It could be a city like maybe Chennai, where we know the data wise 80% of the things are actually landfilled, only 20% is converted into energy, because converting energy also requires investment and pollution is also another issue. So they may have, the municipality might have a policy that all the waste I generate, 80% will be landfilled and 20% will be converted into energy. So the end of life may relate to what is actually possible in a real world situation in a particular regional specifications. Okay, this is something that maybe the producer cannot decide. Okay, so sometimes you have to look at the reality check, what is possible end of life for this product in a given location. Suppose if the same product were to be made in Germany, for example, where the recycling facility, composting facilities are more, you could actually make a change in the end of life option saying landfill is 0%, incineration may be 10%, 90% may be recycled. So that depends on different regional possibilities, municipal, how the municipality handles waste. Okay, so that is something you have to keep in mind. It's highly variable depending upon where this end use is. And in this particular analysis, they are also including transportation, because transportation can add fuel cost, emissions and other waste generation also. Okay, if you remember in the case of resin, in some cases transportation was included, sometimes it's not. So it's very important to know what are the assumptions that are created. Whatever conclusion you're going to derive will largely be subjected to these conditions. Then various other impacts like eutrophication, acidification, other pollutions are not considered. Not considered not because they don't want to consider it, is because maybe the data is not available. Okay, and what are the impacts they have considered? They look at how much fuel is needed, energy is needed, what are the end of life options, like I said, how much material is needed, also waste to energy credit. So what this waste to energy credit means is that whenever you are converting a waste into an energy, you actually get some positive credits for the company, that because you have managed some waste by yourself. Okay, so the company will get a credit for doing this kind of recycling or energy conversion. Okay. Okay, so these are the assumptions. So let's see what is the outcome. So here we are comparing between PLA and the polystyrene, expanded polystyrene or polystyrene foam based on the general purpose plastics, polystyrene, for every 10,000 clamshell products. Okay, so we are comparing only between two materials, PLA and expanded polystyrene. So we have got polystyrene here and PLA here. So first of all, the number of units, both are 10,000. Okay, that's a basis. They calculate the mass of one product. Okay, so for PS it takes about 4.8 grams to make one clamshell, whereas PLA requires about 23.3 grams. Okay, and if you look at the specific gravity or the density of this material, it's about 0.8 specific gravity for foam, and then about 1.25 for PLA. So PLA is more more rigid and more denser compared to foam, polystyrene foam. So you can see that the amount of the mass of polystyrene required and the PLA required are quite different. It's about 5-fold difference in the case. It's because of the foamy nature, the lightweight nature of the polystyrene compared to PLA. And then if you compare the energy required, so we need something about 3034 megajoules for PS, and we have about 13,125 megajoules for PLA. So clearly polystyrene consumes less energy compared to PLA. Okay. What about the carbon footprint, that is CO2 emission? You can see still that PS wins over PLA. Okay. Waste generated, PS generates about 40 kilogram, whereas PLA generates about 187 kilogram. And if you look at water consumed, PS consumes much less water, whereas PLA consumes a very large amount of water. This large amount of water comes because of why PLA requires such a huge amount of water? Corn production. It's coming from an agricultural product. Corn requires a lot of water, whereas PS does not require much water. Okay. So you can clearly see that in this particular comparison, polystyrene it requires less mass, it has a lower energy consumption, lower footprint, carbon footprint, low amount of waste, and very less amount of water consumption. Okay. So we say in this example, polystyrene is more sustainable than PLA. Okay, you say that okay, water is not a problem. What about others? What about CO2 emissions? What about energy consumption? So is it surprising to you? All the while so far we have been saying bio-based plastics are good, sustainable. Now I am telling you a data that actually proves otherwise. What do you mean? No, the inventories have all that. No, you look at energy. Energy is a natural capital. Water consumption is an energy capital. Solid waste generate. Tell me what it is. Yeah, tell me what it is. What is that I missed? Okay. Okay. This alone is not enough to come to a conclusion. Okay, I have a very neutral feeling about this. Okay, fine. What else? What else? Yeah, so yeah, if you change the boundary conditions, yeah, that will change. That will change. But let's say if like I said, that end of life option was fixed by some other constraints. Like I said, the place where it is used, the municipal corporation has that policy. You cannot change that policy. That has a lot of other consequences. So that boundary condition I cannot change. If I change, yeah, I will get different results. But despite that, can we say with this respect, based on this particular table, can we say, okay, let us make our clamshells based on polystyrene than PLA? Of course, we have not put the cost here. The cost of the material has not come in here. I thought someone would say that, that's fine. Okay, maybe cost is not important at this point, let's say. Okay, cost is not an issue. Okay, I can pay more price for PLA but here there's no reason to actually pay more for PLA, because PLA is anyways a losing candidate here. So maybe cost shouldn't be a factor then. So what else? Look at this data very carefully, and I'm saying, so yeah, I mean, keep an open mind. Don't presume that PLA has to win. It's not that. It's not always like that, right? So it's not that PLA has to always win. So keep an open mind. Look at the data very carefully. This is clear data to show foam PS is more sustainable than PLA in terms of CO2, in terms of waste, in terms of water, in terms of emissions. Why are you not agreeing? Yeah, the impact is given. CO2 emissions, solid waste. What do we do? Like I said, no, here this entire thing goes in. Yes. Look, there is that's what I'm saying, there is a CO2 here, you see, that's also going in. Transportation, that's not included here, is it? It says included, no? Transportation is also included. Who will spot the right answer in this table? The key is in this table. Huh? That option we didn't conclude, no? We said we are not recycling, we are only doing a land. We are doing landfilling and incineration. That's it. No other option in this case. So the point is not to change the boundary condition and make a different conclusion. That is not the point. The point is to make sense of this. Better. Okay. That's all I want to hear. So you say, okay, as per this data, PS seems to be okay, and you don't have to have a bad feeling about it. Yes, maybe change the boundary condition, like I said. Change that composting possibility or various other recycling possibility, this conclusion may change. But my take on this was that even without changing that, there is something we can say about it. So that's what I have here. See, this particular LCA did not include the pollution with pollution issues. It didn't say the contamination of soil with microplastic and how it may affect ecological life, eutrophication, acidification. Those things are not there. You see in the table, there is no other environmental impact to soil, to the air, to the water, to the soil. So if you include that, you will see PS will harm the earth a lot more than PLA. But conveniently, they have actually removed that in this particular assumption. Maybe they want to prove PS is better. Could be. Now, another thing I thought you would notice is that the mass of each container. See, for making one container for the same functional purpose, PS requires only about 4.8 gram, whereas PLA would require 23.3 gram because of density difference. But if you try to compare this on a per gram basis, you are then going to have a factor of 5 times more for polystyrene, right? Because this ratio of 4.8 to 23.3 is about a factor of 5. So that means this energy consumed per gram basis, if you calculate, this would be about 5 times more, so 15,000. This only 13,000. Here, carbon footprint 5 times means 0.1, comparable. Solid waste generated, this is going to be 200. This is about 187. This is going to be about 2000 plus. Okay, still less. So the conclusion is largely because we are comparing per piece, not necessarily per mass. Okay, so here the advantage for polystyrene is that you can actually make the same functional unit with a less material, and you're not comparing unit mass based, but based on the function unit itself. So in that context, and subtracting all the pollution index, you can actually show in this case polystyrene can be a winnable candidate, right? Okay, so while you are in that shock, let's go to another another example where something else is proved now. Okay, this is from another company funded by another company. So as he was saying, generally if I'm a PLA company, PLA producing company, I would hire a LCA consultant and I'll ask, okay, this is what I want to produce, give me LCA report, and maybe my client will understand I need to prove PLA is best. So there will be some sort of vested interest, okay, so that we have to always keep in mind. Because most of this detailed LCA analysis is actually published, or the reports are given by companies which actually make plastic products, not academic institutions. If you and I were to make this LCA, we would be unbiased, okay, because we don't derive any benefit of making that products. Okay, so you have to be very careful about this analysis, who has done it, for whom it has done it, and all that. Okay, so now let's go to the second aspect. Again, we are talking about same disposable food container product. Again, reference is here. So this LCA is done by a company, IFEU, German-based company. It is done for a company called NatureWorks, which is the largest producer of PLA in the US. Okay, so the report is submitted to LCA NatureWorks. The reference is given here. So what are the assumptions? Okay, so here the basis unit is 1000 clamshell container containing 500 ml of capacity. So here the volume is kept constant. How much it can pack, that volume is kept constant. In the previous example, that was not considered. Okay, the masses are different, the containing capacities are very different. So here they want to make sure that all of this container should have 500 ml. What are the material choices? They have the oriented polystyrene, it's a different kind of polystyrene, polypropylene, PET and PLA. So here we are trying to compare between a bio-based PLA versus fossil-based non-biodegradable plastics. What are the cradle to grave analysis? So here this end of life is actually chosen differently for different plastics. For example, landfilling 80%, waste to energy 20% for all the conventional plastic like polypropylene, PET and polystyrene. Whereas when it comes to PLA, they say 80% can be composted and 20% can be recycled. This itself should tell you PLA is going to win, because there is no waste created by PLA largely, because 80% of them actually composted, that it basically goes back to soil, and then 20% are actually recycled, put back into the product again. Whereas if you look at this PP, PET, OPS, 80% is landfilled and 20% is incinerated. Again, this is also probably related to the region where it is applied. So the municipality which handle this waste probably is able to distinguish between PLA and non-PLA based products, and they may have a segregation mechanism where all the PLAs are taken out, and then that stock goes for composting and recycling, while the rest of the plastics are landfilled and incinerated. So this probably is a requirement or the option available in that particular regional space, right? If you look here on the other hand, they have looked at all the environmental conditions, acidification, other pollution, and eutrophication. Why? They want to include this specifically because we know that all the fossil fuel based plastic will actually make a negative impact on this, and PLA will not, because PLA is handled. So, you will clearly see that this assumption is set such a way that PLA has to win. Okay. In other words, other way of saying this is that PLA can actually have a better end of life compared to other plastics, and transportation is also included. Okay. So, these are the assumptions. Let us go back to the table. So, as I said, numbers. So, we are comparing between 1000 clamshells made up of PLA, PET, PP, OPS, all having 500 ml capacity. Okay. So, that the first row is the same because of the basis unit. If you look at the weight, you see the weights are again different, mainly because the volume is kept constant, but you can make in different masses because the densities are different. Okay. Each material has a different density, that is given here, right. Energy consumed, you see PLA has the lowest among the lot. If you look at carbon footprint, again PLA has the lowest, and polypropylene something next to it. And then if you look at solid waste generated, PLA has a less waste generated compared to other two. Water consumed, of course PLA consumes more water because of corn, right, corn production, whereas others are and PS also has next biggest thing. And then eutrophication of water, soil, acidification, in all those counts you see that a PLA is relatively better, but there are a couple of examples. For example, if you look at acidification compared to PLA, PP seems to be better, but in other counts it fails. So, therefore, you can say PLA can be used with thinner walls due to high Young modulus. Okay, what I mean by that? So, if you compare here, if you compare these two, PLA and PET, PLA and PET, you are making same volume of container. The mass of PLA required is only 12 gram, whereas PET is close to 20 gram, even though the densities are very similar. That is because with the PET you have to make more thicker wall to give enough strength to hold that product, whereas PLA has much higher Young modulus. Even a thinner walled container can actually support the same functional properties. Okay. So, sometimes we can actually make use of this material property to minimize the amount of mass that we need to create. Okay. So, that is something that we can think about. So, to summarize, we say that in this particular comparison and assumption that we have created, PLA seem to be a better candidate compared to OPS, PET and PP. Third example, again clamshell. Here 1000 clamshell is the basis, and the design is to hold, you should have enough volume to hold about 553 gram of strawberry, okay, something like this. Again material choice, PS, PET and PLA. This is from a different LCA group, different report. So, CIMA Pro LCA software is used. So, here cradle to grave analysis with a very different kind of end of life. So, here the landfilling is 76.5% and waste to energy is 23%. PLA is not composted here. In the previous case, PLA was allowed to composting and recycling was allowed, but here PLA is not composted. So, PLA is also actually landfilled and converted into waste to energy, again maybe because they are looking at a particular option of what is there. Again all the pollutions are considered, transportation all included. Okay. So, you can see among these three the assumptions are largely similar, but there are some key differences also that you have to watch out for. So, here what we see is that basis unit 1000, and if you look at the mass, you see they are a little different depending upon the the container thickness and all that. Specific gravity is given. So, if you look at energy consumed, so PLA has the lowest energy. Carbon footprint also is comparable to PS and PLA. I mean 1.65, 0.165, 0.171, not very different. And solid waste generated is less. Water consumed as always is more because as we said corn will consume some water. And then if you look at the pollution parameters, acidifications, they also seem to be relatively better, even though in this case PLA is not composted, okay, it's still landfilled, okay. Despite that, this comparison seems to be fairly towards PLA, right. So now I think you should be more comfortable. PLA seems to be a little better option, when we consider the environmental effects. The first one did not consider that, right. So here if you look at the acidification and eutrophication of water, soil pollution, acidification, then PLA definitely is a winning candidate. So this one, the fourth one is trying to compare between PLA, which is bio based, PET, which is fossil based, but also considering a recycled PET. PET is one of the highly recycled material. So here if you can mix rPET based recycled PET based material, what is the impact? Assumptions: 1000 clamshell of equal volume, material choice as I said PLA, PET and rPET, and the cradle to grave analysis. The end of life option is the following. They have got different options for different material. As far as PET is concerned, 40% is recycled, okay, remaining 60% is landfilled. When it comes to PLA, 5% is composted, the remaining is landfilled. So you can see that you can make different choice for different material. That's because again how we manage waste, whether we're going to group all of them together and landfill, or we're going to segregate and then manage one particular waste differently, okay. So PLA can be identified, segregated, managed differently. Again, all pollutions are considered, transportations are considered, okay. So let's see what we get from here. So here, so this means PLA with the 5% composting means that when the PLA is wasted, 5% of that product is actually composted, the remaining 95 is landfilled. When you have this PET, you have 40% that could be recycled, okay, and then you have virgin PET which does not have any it's virgin PET basically means it's a fresh PET resin from the polymer industry. Okay, so what happens here? So we have let's start from energy. So if you look at energy, it seems that the 40% recycled PET seem to have a lowest energy compared to PLA, and if you look at emission, PLA seem to have the lowest emission. In terms of solid waste generated, PLA is lesser, and eutrophication of water again lesser. Acidification, in this case as you can see, PLA has more acidification than virgin PET and rPET, and then they have given some few other things like ozone depletion and ecotoxicity and other things, okay. So the way that this study was done, initially the study was made with 100% landfilled, they got a different result. Now they optimized the end of life option such a way that when PLA will become a winning candidate. So they found that 5% composting if you can do with PLA, it can actually outweigh the recycled PET case. Again, as you can see, it's very dependent on the boundary conditions. We should not lose hope here saying that anything is possible. That's not what we are saying. I'm just saying that there seems to be a multiple optimal point that depends on the material choice, the container specification and the end of life options, and whether you want to include the pollution information or not, okay. So depending upon all that, so this is just I'm trying to summarize all the LCA that are there in the literature that compares between various boundary conditions and assumptions, right. Okay, I think that's all I have. What I would do is so this is I will upload this data. You can take a look at this. Look carefully the table. The table is very important, and see what you learn from this table. Okay, so like I said, many times it's not like one product always wins. One product may actually have few options better compared to other. So in such a cases, we have to make a decision: can we compromise on the energy consumption, or can we compromise on the emission? Which one should we, which one can we tolerate? Which one can we allow? So those are the decisions that one has to make. There is no thumb rule. It depends a lot more on economics. Economics is not at all coming in here. That also has to be factored in. What we are doing is a life cycle analysis. There has to be a financial analysis also. Okay, so it has to go hand in hand with LCA and the profit loss calculations. So subsequent to this, I will in the next lecture I will talk about grocery bags. Okay, grocery bags all of us use. Again, you can think about paper, you can think about plastics, and you can think about cotton, right? Cotton textiles, cloth bags, a lot of things. So what is your assumption? What do you think? Paper versus plastic, who will win? Huh? In terms of sustainability? Huh? Paper. You see, right, in grocery, if you go to Phoenix Mall, most of the retail outlets are now giving your things in paper bag because they think it's sustainable, but actually it's not. If you look at the amount of water that you need for producing, is actually, I will show more data in the next class, that paper bag will only win if you include the pollution aspect to it. Okay, otherwise the amount of water, amount of energy, amount of emissions, if you look at it, paper is not the most sustainable, but actually we have a perception to think paper is degradable. We always think in terms of degradability. We don't see paper lying around in the waste bin for very long, but plastics do. So it creates a different perception in our mind. But if you do an LCA analysis, you will see that our intuitions are not necessarily correct, right? So I think it looks to me, in terms of I mean, I don't want to preempt your thinking and understanding, but in my mind I see that in terms of cost we cannot beat plastics. Okay, in terms of the properties, the kind of things we can make with the plastics, we cannot beat with any other material. If I can somehow manage the pollution aspect of it, then I think plastic is the best case in terms of economics, in terms of sustainability. I think plastics lose big time only in the case where we don't manage it properly. Composting, incineration, landfilling, these things have to be revisited. If you have a best case scenario where all the plastic I produce can be somehow be degraded or recycled, then plastic will be the hero. Okay, with that I'll stop here and let you think about this information.